Start streaming and stop recording. No, we're good. Yeah, well. Yep. Alright. Let me connect to that stream thing. Yeah. I gotta connect to the air server so I can use my iPad. It'll take about an hour today. It ain't gonna be super long. Let's see here.
What setup are we going to need to do with balance?
Let's see. Screen mirroring. Classroom. Well, it says I'm connected, but it's not showing anything. Alright. That's an issue. Let's try the sum. Oh. I was connected to the wrong one. Isn't that handy? Alrighty. So today we're going to be talking about motor drives. Let's see here. So, what is a motor drive? You know what a motor drive is, right? Being silly. You really don't know?
I mean, I know that it sends a signal to the motor to make it run.
Okay. So, like, the technical definition is an electronic unit designed to control the speed of a motor using solid-state components. And it can control motor direction, speed, and acceleration. That's just the basic, though. Like, they can get really in-depth. Like, they can control a lot of stuff, depending on how they're programmed and if they're a basic drive or an advanced drive, stuff like that. Okay. And AC drives have become the most common because they easily vary speeds of a three-phase motor while only requiring one phase, 115 or 230 volt, and if they are smaller drives, less than 3 horsepower. Alright, now let's see here. So most drives provide display info like voltage, current, frequency, drive temp, faults, phase losses, advanced programming features, and those features include setting multiple preset speeds, limiting motor max and min speeds, and motor braking. We'll go over some of that more in depth here in a minute. Pretty much, yeah. Like, once you have all that wired up, you can control everything through that drive. That's why they make your life easier. You know what I mean? Like, you don't have to wire it up a certain way if it's wired up correctly with the VFD. So, let's see. So, motor drive control circuits. The drive is wired by following the control circuit. Robbie tried calling me. So that must mean I'm not streaming. Or maybe you can't hear me. Hey.
Do me a favor, make sure to let everybody know in your classes that if they don't wear proper PPE for what they're doing, that they're going to get turned out to go get some. Okay?
Okay.
All right, because I don't want the same thing to happen this week that happened last week. Cool?
I sure will. I thought maybe you was watching a live stream and you couldn't hear me, so I hope you can hear me.
Oh, no, I haven't been. I've been driving home.
All right. Well, I think everything's working good. I'm supposedly streaming and recording, so I guess we'll see.
Okay, cool. All right.
Thank you. Bye. Anyway, okay. So one main advantage of using drives instead of a motor starter is that drives offer better speed control. So it's more reliable than just say like a magnetic motor starter. What is a potentiometer? Do you know?
The speed, current, or voltage of which something.
A variable resistance electric device that divides voltage proportionally between two circuits. So let's see here. Motor drives are programmed to control a motor by setting various parameters. So basic motor drives can contain around 30 parameters, and advanced can contain up to 100 parameters. So you know what parameters are, like if the motor hits this voltage, do this. Like it's like a set of rules, and you know, like it shouldn't go up but to this voltage. Like, so if it hits over 60 volts and it's set to 60 volts, it's going to trip the motor. You get what I'm saying? So parameters just means like a set of rules or components of what that drive would be made up of. When drives are used in a system, troubleshooting can be more difficult and time consuming. So what are some faults we might see in basic motor drives, do you think? Just rack your brain. What do you think we might see? So like just like think, yeah, so not even with the drive. That drive is going to have a fault if, say, there's like under voltage, over voltage, phase loss, right, stuff like that. So here we go. We got power loss, over voltage, under voltage, motor overload. So it's going to say, hey, you're working too hard, like we're about to trip you off.
So would you have to run an overload drive, or is it?
Now that's a good question. Like I'm not going to say yes or no to that because I'm not quite positive if there's. I'm sure there are VFDs with already built-in overload protection, but I'm guessing just like what we've seen already, different contactors, like you know, have different settings, and so they're made up of different components. So I don't want to say yeah or no to that. It's probably just depending on what kind of variable frequency drive you have. If it's an older one, you might have to include overload protection, but I'm sure nowadays it would be assumed that most things do come with overload protection because we know that that's a good way to protect your equipment, right?
Yeah.
So I would assume so, but I don't want to say yes or no to that. You know what? We can just Google it. Let's just Google it because I don't want to say that and then me tell you wrong. So let's just say, do VFDs have overload protection built in? Overload protection built in. They have adjustable overload parameter to protect the motor.
So you can adjust the temperature.
Yeah, so drives come standard with electronic thermal overload protection, allowing the VFD to deliver 150% of the rated output current for 1 minute and higher current levels for shorter periods. So the overload can be adjusted to protect smaller motors too. So I guess you just set the parameters like you don't want it to go over this temp, you don't want it to go over this current or this voltage, stuff like that. All right. So what is a VFD? We already know that that's a variable frequency drive, and it's a device that controls the voltage and frequency that is being supplied to a motor, and it improves system efficiency. So VFDs are capable of adjusting both speed and torque of an induction motor. Do you remember what torque is? Okay. Just for when we went over motors, I know it's been a few weeks. So, and it provides continuous range process speed control, and sometimes referred to as AC motor drives, variable speed drives, adjustable speed drives, inverters, etc. So they might be called different things, but they're all VFDs. So, just always remember that if they're calling it something different at your job or whatever, it could be any of those names, but they all basically do the same thing.
Anything that's called electronic drive.
So no matter what it is called, its job is to convert incoming supply power to an altered voltage level and frequency that can safely control the motor. So no matter if it's an AC drive, inverter, variable frequency drive, whatever, it is always going to convert incoming supply power to an altered voltage level and frequency. Okay? And so just a good rule of thumb is the lower the frequency, the slower the motor speed. Okay, so let's just show some examples here. So if a motor is rated for 1730 reps per minute at 60 hertz, how many RPMs would it produce at 60 hertz? It's not a trick question. What would it produce?
Oh.
1730.
Oh.
It's rated for 1730 RPM at 60 hertz.
Okay.
So how many RPMs would it produce at 60 hertz?
1730.
Okay. So now let's see, it's going to be 1730 RPMs. Cool. So now, what about 30 hertz? Let's see if you get it right.
$865.
Boom. Cool. All right. Now, how about 15?
$432.
There you go. So you get it? Cool. So it is going to produce however many hertz it's set for. So that's just showing like a parameter example. So if a motor is rated for up to 60, it can produce up to 1730 RPMs. But if you, depending on the application you're using it, you might only need it to, you might only need it to produce 865, so you're going to set it at 30 hertz. Cool? Understand it? So the lower the frequency, the slower the motor. Okay, got that?
Yep.
All right. So the three main sections of a motor drive. So the first main section of a motor drive is a converter, and it receives incoming AC voltage and changes it to DC voltage. So if the input voltage is different than the output voltage, the converter must step up or step down the AC voltage. So a drive is supplied with 115 volt AC and needs to deliver 230 volt AC. What would happen? So what would we do if that happened?
Step it up.
Right, we're going to step it up with what? A step up transformer? Right. We would use a step up transformer to increase the voltage. I had that on the bottom. I guess I meant to show both of those at the same time, but we would use a step up transformer to increase the voltage. Okay? See how it's all kind of meshing together now, isn't it? That's why we go over a little bit, bitty bits at a time, so it starts making more sense later on down the road. You know what I mean? So let's see here. The DC bus filters the voltage and maintains the proper DC voltage level. And it may also deliver DC back to the inverter for conversion back to AC. So, what's a capacitor? Do you know?
Been 8 years since I've had it.
So a capacitor is an electrical device designed to store a voltage charge by means of an electrostatic field. And capacitors are used in the DC bus to filter or smooth the voltage, so it helps with voltage fluctuations. So if voltage was dropping really fast, that capacitor would kick in and it would increase the voltage back. So the third part of the drive is in the inverter, and that changes the DC voltage back to AC voltage. That way it can be used in our common applications today. So most important part of the drive, because the inverter determines the voltage level, voltage frequency, and amount of current that a motor receives. So here's some motor stopping methods. Ramp stop, coast stop, DC brake stop, and soft stop, which is also called S-curve. So I put load right here because that's dependent on the load, how fast it stops. The rest of these are dependent on the drive. Okay, so these three are going to be stopping dependent on when that drive wants it to stop. This is dependent on load, okay? Coast stop is load. So ramp stop, level of voltage applied to a motor is reduced as the motor deaccelerates, and that's normally the factory setting on a motor, or on a drive, unless otherwise specified. So coast stop, motor drive shuts off the voltage to a motor, allowing the motor to coast to a stop. So that's kind of just saying we're cutting off all power and we'll let you stop when you feel like it. So it's just going to coast until literally the motor has no more energy, right? And then DC brake stop. A DC voltage is applied to the stator winding of a motor. And do we remember what the stator is? It's a stationary winding, right, of a motor. And the soft stop, or S curve, the programmed deceleration time is doubled and the stop function is changed from a ramp slope to an S curve slope. So that means it's just going to let it it's going to stop fast, but it's not going to just like stop it so fast that it damages the equipment. Alright. And now I was just going to read out of the book a little bit and maybe talk about some troubleshooting methods and stuff like that, because I didn't want to overload, you know, the drive thing. Because drives are important, but anything you talk about too long can be too tire you out, and you're not going to pay attention to it after that. You know what I mean?
Yeah.
I had some pages turned down in here. I should have used my sticky notes. And I am going to put a test on Canvas this week, sometime to do. And it's going to be open book, but there's not going to be any information on Canvas like for you to look at. So it's going to kind of be like something if you don't pay attention to the lecture, or, you know, if you don't like read, then you're not really going to know what's going on. What in the world? There they are, back here. I knew I was overlooking them. Alright, so this is just some stuff I didn't want to overload on there. So, you don't have this book, do you? I didn't think so. Alright. We've went over potentiometer. Here's this page. So, let's see. Advanced program. Alright, so here was some of the parameters I wanted to go over for, like, say, you know, hang on. Don't know, I'm trying to get out of my mouth here. Being crazy. So, like, basic programming parameters of, like, a drive. So I wanted to go a little bit over the programming because that kind of interests you, doesn't it? Like, programming stuff. So, like, the basic parameters. So, basic parameters of the programming of drives was going to be like, so they normally require technical information listed on a motor nameplate. So they're normally on the nameplate. So like if that motor is rated to a certain temp, that would be in the parameters. Like I know we've done said that, but it doesn't hurt to say it more than, you know, once. So say like the nameplate, like voltage, current, frequency, let's see, the desired acceleration time. So how long do we want it to take for this motor to get to operating at full capacity, right? And then deceleration time. I don't even know if I don't think I spelled that right, but whatever. Deceleration. Oh, and the stopping mode. That could be a parameter. So, do we just remember the modes we just went over? So, like, what would it be? Either ramp, coast, or the S curve, or DC stop. So, one of those would be, or DC brake, sorry. So, whatever stopping mode you wanted to use, you would, also program that into your drive. Then, if we wanted to move on and say advanced, because those are pretty basic, right? Like, you can see all those on your nameplate. So, if you just wanted to control like a VFD, like in the lab,
Yeah.
it would just be, whatever's on that nameplate. You wouldn't want it to go over that for whatever the motor was rated. But then again, we might not be wanting to use the full capacity of that motor, so it might be we just need, that right. We don't need to produce as much as it's rated for. So, all right. So then you get on into advanced programming parameters of a drive. It says, although basic programs normally allow for good motor drive system operation, there are applications that require special operating conditions. So, advanced program parameters allow for customizing a motor drive application. So, sometimes they can include, drive output contacts operation. I know my handwriting sucks. And that is just like when a motor is at set speed and during motor acceleration. So, and then multiple acceleration and deceleration times. So, like, if you needed it to accelerate at a certain time or under certain circumstances, then you would have to do that more advanced. Like I said, like the set rule thing. Like, once it reaches this, we need to decelerate. You know what I mean? If I'm confusing you, just let me know. Are you catching on pretty good though?
Yeah, it all makes sense.
All right. And then preset motor speeds and type and time of braking applied to motor. All right.
So when you do this programming, say like, you're looking at that onto a computer.
You said like from an Ethernet, from a
Yeah,
computer?
like-
I'm sure. Like, we can look at videos here in a minute if I can actually get on the internet, which I may not be able to. But, we could look up like how to program VFDs and stuff. But I don't know if I can get on the internet. But I'm pretty positive, like, depending on like the VFD program software that you would buy. So like if you say you bought an ABB or whatever, I'm sure it would come with its own programming software that you would download and then literally just do it all on your computer, iPad, whatever, and then download it to your VFD if it was advanced. But I feel like if it was some VFDs, then you could probably just do it on like the little menu pad. You get what I'm saying? So if it was like basic programming, but I do feel like the more advanced obviously is going to have to be in a program on a computer or something, and then you download it to the VFD.
Yeah.
Because there's no way you could do all this on one little tiny screen. You would be having to, you sit there for hours, you know what I mean? So, it also prevents motor from reversing or going forward. So, it just prevents it from going in the opposite direction of what you want it to. So, number of times the motor drive attempts to restart a motor after a fault, that could be an advanced setting. Analog inputs. Let's see. So basically you're programming all of this to where if it has a fault, you know exactly what the fault is. That's how I would want to program it. You know what I mean? Like, I'd want to program it to where it would show me a fault of something pretty basic that I could understand instead of having to get all squirrely and go down a rabbit hole. You know what I mean? So now we're about to get on to fault codes. We've already talked about that, but like fault codes, this is like an example of what a fault might read. And so the number of the fault might be F2. So I'll just go ahead and write this down because I know you like seeing it. So the number of the fault might be like, say, F2. But the fault would be auxiliary input. And so in your description, while you're programming that, you would want to put something that is like a hint of what might could be going wrong. You know what I mean? So you would want it to be like check remote wiring, right? So that would tell you exactly which wiring to check when that fault comes in. So another example would be like the number would be, let's just see, F7. And that is your motor overload. Now these are all just examples, okay? So that would be your motor overload. And the description of that is an excessive motor load exists, reduced load, so drive output current does not exceed the current set by parameter P033. So see, that already refers back to the parameter you set. So it's kind of telling you like, hey, you know, this motor is exceeding that parameter P033. So unless you want to keep getting this fault, you're either going to have to edit that parameter or set the motor to not produce as much. So do you kind of get it? Like, it does make your job easier. It kind of sounds complicated, but
It seems pretty simple.
I mean,
Compared to, like, wiring up a contact.
yeah, like once you get that contactor wired up, you don't have to wire it up 50 million times for 50 different applications.
Yeah.
Once you get it wired up, you literally can control everything through logic and VFDs and stuff like that. Like, that's why those things are so important, because back in the day, they only had, you know, basic stuff. Like, they had to go out there and troubleshoot and see, well, did somebody wire this up wrong? But now it's like you got a VFD or a logic controller or whatever telling you exactly what's the matter. So it makes troubleshooting a lot easier. So it makes your job literally easier. And once you get to see it in person work, you'll be like, oh, this is way better than wiring up that push button.
Yeah.
So let's see. Let's talk about some, even though they're not as common, DC motor drives. They're not nowhere near as common as AC because they're more expensive, and dealing with DC motors, you know, they take more maintenance. So there's not too many places that have DC motors unless it's like big industrial applications and stuff. But you know what I mean? Like, you're not going to have a lot of DC motors in the industry.
Yeah.
It's mainly going to be AC. And so, like, anyways, that obviously means that DC motor drives are not as common as AC, because we've already said that AC are the most common. So they're the cheapest, they're less maintenance, and that's because AC motors are cheaper, less maintenance. They don't have all the brushes and, you know, stuff like that that has to have preventative maintenance done on it. Yeah. So, but DC motors are normally used in applications that require precise motor speed control. However, since AC motor drives offer comparable speed control in most applications, AC is used where DC motors were once used. So that's what we was just talking about. Like, AC's pretty much the bigger, better version, except it's smaller, better version of a DC motor. So, DC motor drives use electronic controls to vary the amount of DC power supplied to a motor. So motor speed is controlled by controlling the voltage to a DC motor. The higher the applied voltage, the faster a DC motor rotates. So, let's see. So motor torque is controlled by controlling the amount of current in the armature of a DC motor. And like, you can go all down this thing, but we're not going to be, I don't think we're going to be messing with any DC motor drives and motor controls. So that's why I didn't really want to like get deep into that.
Yeah.
But, just to compare like the two. And so let's get into dynamic and regenerative braking. And this is to do with DC too, so we're not going to really talk about it much. I'm just going to give you the definition of it. So dynamic braking is a method of motor braking in which a DC motor is reconnected to act as a generator immediately after it is turned off. And then regenerative braking is a method of motor braking in which the regenerated power of a DC motor that is coming to a stop is returned to the input power supply. And we're not going to talk about that anymore. So, moving on to what we've already talked about, AC motor drives, just as a summary here. So they can be referred to what other names that we mentioned besides variable frequency drive?
Well,
So, like AC motor drives are referred to as variable frequency drive, which is VFD, obviously, adjustable frequency drive, inverter drive, vector drive, direct torque control drive, and closed loop drive. So if you hear any of those names, if you hear it called any of those names, then you know that it just basically means AC motor drive. So they're all doing the same thing, right? Always. Hang on, let me open my thing back up. So we said that no matter what they're called, their job is to convert incoming supply power to an altered voltage level and frequency that can safely control the motor. Okay? So remember that. That might be on a test. So what's their job? Convert incoming supply power to an altered voltage level and frequency. And I'm not going to specifically ask for you to name off all those, alter names or whatever, but I would at least like you to remember a few of them that way in case you hear them in the industry. Instead of it just being called a VFD, somebody else might refer to it as a vector drive or an inverter drive or whatever.
Yeah.
So just remember at least 2 examples of those because that might be on a test too. Okay, you get what I'm saying?
Yeah.
So what's the 3 main sections of an AC motor drive that we talked about? So we said converter, inverter, and the DC bus, right? So that's the 3 main sections of an AC motor drive. Converter, DC bus, and inverter. And so, do we remember what the converter does?
it converts down.
AC to DC. So it converts, it's an electronic device that changes AC voltage into DC voltage.
Then an inverter will be.
An inverter is the exact opposite. So a converter changes AC to DC, inverter changes DC to AC. And I'll even write that on here so we can see it one more time so we can remember that easier. Oh, you dirty thing. I don't know what I'm doing here. There we go. So if we have inverter, it goes from what? DC to AC. And then converter is the exact opposite, which means it goes from AC to DC, right? So AC, DC, the band, remember that's converter. And then inverter is the exact opposite of a converter, right? So always remember just AC, DC, the band, and relate that to converter, okay? And then, let's see. So, really? So, now, talking about the converter. Some of the requirements of a converter. So, in order for a converter to deliver the proper DC voltage to the DC bus of an AC motor drive, the converter must be connected to the proper power supply. So, AC motor drives operate satisfactorily only when connected to the correct voltage level and frequency. It must also provide enough current to operate an AC motor drive at full power.
So you would run, say, that AC motor. So if you had a three-phase motor, you would run three-phase power to that drive.
So not necessarily. So like, so we was talking about earlier about, so they're designed to operate three-phase AC motors, regardless if they're designed for one phase or three phase.
Okay.
Single phase. I know I said one phase, but three phase or single phase, like they're designed to operate solely on three phase. So, that would be 115 or 230. Okay. And I'm talking about volts AC. You know that, right?
Yeah.
So 115 volts or 230 volts. And so if the application required, we already said that if it required less voltage than what was going into the drive, that drive is either going to have to step it up or step it down depending on what that motor is calling for, right?
Yeah.
So, yeah. They're always designed, or they're made for running three phase. Even if they're designed for single phase, I know, which makes no sense, but I guess they can run both ways if they're designed for a single phase as well. But the more efficient ones are three phase. I don't know if that answered your question. I might have went crazy. But let's see. Now we need to move on to talk a little bit more about DC buses. So they filter and maintain the proper voltage level. Let's see. And so, talking a little bit about circuit protection. Do you know what transient voltage is? So, transient voltage is a high energy, high voltage, short duration spike in an electrical system. So, we'll go ahead and write that down too. So, transient voltage. And that is just a basically short duration spike in an electrical system. And so to give you an example of what transient voltage might be, so like say lightning strike, right? That would be transient voltage because that's just a very short duration, quick spike in voltage, but it's enough to damage equipment, right? So, let's see. So like lightning strikes and utility switching cause high energy level transient voltages. High energy level transients seldom occur, but are quite damaging to equipment if allowed to travel through a power distribution system and into electrical equipment. So like lightning strikes your meter at the house, like that's going to destroy it, right? If it didn't have the right protection. So low energy level transients are transient voltages commonly caused when motors and equipment are switched on and off. So low energy level transients occur often, but do not cause immediate equipment damage. Low energy level transients cause malfunctions such as processing errors and damage to equipment over time. So the electronic circuits of an AC motor drive require protection against transient voltages. Protection methods include proper motor drive wiring, grounding, shielding from power lines, and surge suppressors. So a surge suppressor, I cannot talk today. Surge suppressor is a device that provides protection from transient voltages and let's see, by limiting the level of voltage allowed. So like that's what you would call like, you know, you always have like surge protectors and outlets and stuff like that. Or like, especially on your computers, like at home. I don't remember if you ever remember growing up, but there was always surge protectors on computers because like people were scared to death that 1 in a million lightning strikes would hit their house and like, you know, destroy their computers or whatever. My granny always had a surge protector on her computer. Let's see. We've already talked about a capacitor. It's an electrical device designed to store a voltage charge by means of an electrostatic field. Capacitance. So we can write this up here too so you can see it. Capacitance is the ability to store energy in the form of an electrical charge. Okay, cool. And what does the inverter do? Yep, you're right. Converts DC to AC because the converter does AC DC, and that's the band, right? Okay. And so inverters in an AC motor drive are the most important part of the drive because the inverter determines the voltage level, voltage frequency, and amount of current that a motor receives. So we need to step on this a little bit. So go down here. So voltage and frequency. So if the voltage applied to a stator of an AC motor, the voltage applied to the stator of an AC motor must be decreased by the same amount as the frequency. So they need to be decreased at the same amount. So if it decreases by 10, it needs to decrease by 10. So decrease the same amount. Which it would make sense because we said earlier, the lower the frequency, the slower the motor goes, right? So you would want them on the same page because you wouldn't want it to be all out of whack and, you know, it's producing more than it's supposed to be or whatever. So the motor heats excessively and damage occurs to the windings if the voltage is not reduced when frequency is reduced. So it's going to damage the motor. All right. And let's see. The motor does not produce its rated torque if the voltage is reduced more than required. The ratio between the voltage applied to the stator and the frequency of the voltage applied must be constant. So we understand that voltage and frequency need to be consistent with each other, right? And that's telling you right there that, you know, you need to program your drive to go to that motor consistently. So it's like if you're setting it at 60 hertz to equal 1730 RPM, it needs to be consistent. So like the example I showed you, it needs, if you cut it in half, the RPMs go in half.
Yeah.
Or the voltage goes in half. So let's see. We're not going to go over that. Ooh, we've already went over the motor stopping methods. So one more time, because it's probably going to be on the test. What are the 4 methods we went over for motor stopping? Ramp. So ramp stop. So, and that method is the level of voltage applied to a motor is reduced as the motor deaccelerates. So that's normally the factory setting. That's the S-curve one.
Oh, that's.
Yeah. So the length of time the motor drive takes to stop the motor is controlled by the deceleration time parameter in the motor drive. So the default setting for the deceleration is normally 10 seconds, but it can be set from a few seconds to several minutes. So depending on the type of motor, equipment wear and tear, stuff like that. Yeah, that would all depend on the nameplate info and like what parameters you was setting it as. So you might want it to shut down in 10 seconds, like if it was a safety stop. But then again, you might not care if it coast stops, you know, if it wasn't a dire situation. You know what I mean? But if it was an emergency stop, you'd want that motor to stop within a few seconds, right? So coast stop is a stopping method in which the motor drive shuts off the voltage to a motor, allowing the motor to coast to a stop. So when that method is used, the drive does not have any control of the motor after the stop command is entered. So that motor is just willy-nilly. It'll stop when it feels like it. So, and then DC brake stop, we talked about that one, and it's also called DC injection braking, is a stopping method in which a DC voltage is applied to the stator winding of a motor after a stop command is entered. So unlike ramp stopping, the applied DC voltage is held at the level entered into the DC hold volts parameter on the motor drive. So the applied DC voltage is maintained on the motor stator for the length of time entered into the DC hold time parameter on the drive. So that method provides a fast stop and can apply a braking force to hold the motor after the motor is stopped. However, the DC brake motor stop method cannot take the place of a friction brake in applications that require friction braking. And then let's see, the soft stop, aka S-curve. It is a method in which the programmed deceleration time is doubled and the stop function is changed from a ramp slope to an S-curve slope. So the soft stop method provides a very soft stopping operation. A very soft stop may be required to prevent light loads, such as empty cans or bottles, from tipping. So that would make sense. Like if it was on a assembly line, you know, as an example, and they was wanted to come to a very soft stop, they would use the S-curve method. Because they would want to be like, okay, we're just going to very smoothly come to a stop. Like, you wouldn't want to use the DC brake stop that's like, skirt, because you're going to like destroy your assembly line, right? All right. We're about done. I just wanted to go over some troubleshooting things with ya. Let's see. So, let's see here. So just like a few little like reminders like for troubleshooting. So I'll write this down too so you can see it. So I'm not just reading out of the book. But so like say you was troubleshooting your drive. And here's some things that might help you along the way or whatever. So troubleshooting is a systematic elimination of the various parts of a system or process to locate a malfunctioning part. We already knew that. So when a motor circuit is not operating properly, voltage and current measurements are taken to help determine or isolate the problem. So voltage or current readings. I know y'all get tired of constantly hearing about troubleshooting, but that's what you're going to run into when you're in the field. You're always going to be having to troubleshoot something. So it's good to stay on top of like the methods of troubleshooting, you know? So let's see. So voltage measurements are taken to establish that the voltage is present and at the correct level. So voltage is present and accurate. So if that's true, then you can mark that off your list and say, okay, we've got voltage and it's measuring what it should be. I can move on to the next thing. And that would be, let's see. I'm sorry. My brain ain't working today. Let's get back to voltage. So voltage might, taking voltage measures, bleh. See, I'm telling you, I'm not working right today. Voltage measurements may help determine circuit problems such as like blown fuses, improper grounding, contacts not closing, etc. Right? Which I know this is pretty common stuff, but sometimes it's good just to hear things a million times so it's ingrained in your head. So when you actually need it, you'll be like, oh yeah, I remember hearing this 50 million times in class, right? All right. And then, however, voltage measurements alone do not indicate the true condition of a motor because the voltage may be correct at the motor terminals, but the motor may be faulty. So, when voltage measurements are taken, the required protection and safety equipment should always be worn, and the proper and safe procedure should always be applied. And then it just tells you how to measure voltage. And we already know how to do that. So, and here's how to reverse troubleshooting reverse circuits. Alright, I'm about to read you just one last thing and then we'll be done, okay? So, motor drives provide energy savings when used with variable speed and variable torque loads. Motor drives are commonly installed on pumps and fans and HVAC applications. When a motor drive is installed to control a pump or fan motor, the speed of the motor can be varied to control the flow rate of the pump or fan, allowing less energy to be used. So reducing the amount of energy used by pump or fan motors reduces the utility bills of a facility and also reduces the emissions of greenhouse gases from power plants. So that's why you'd see a lot of VFDs in power plants and stuff. And motor drives provide a number of performance benefits over standard motor control systems. The benefits of motor drives include significant energy savings, precise control of motor and speed torque, and elimination of high starting currents and high transient voltages, resulting from large motors turning on and off because motor drives ramp up motor speed when starting and ramp down motor speed when stopping. And the last paragraph is, motor drive manufacturers provide software programs to calculate the cost savings realized when using motor drives with pumps and fans. Info such as motor horsepower, motor efficiency, cost of electricity, cost savings program calculates the annual cost savings and the payback period. In many cases, the software is available free or as a download from the website. So that kind of answers your question from earlier. It's going to come with software already. So, but yeah, so do you have any questions or anything? So, 3 main sections of a drive. The last one, DC bus. So, converter, shit, isn't it? So, we got converter, inverter, DC bus. So just think about bus, okay? It's a DC bus. That's the 3 main sections of a drive, right? And the most common drive is an AC drive, also known as VFD, vector drive, all kinds of different stuff. Adjustable drive, adjustable frequency drive, stuff like that, okay? And then, so they make your life easier when it comes down to the parameters you set. So like on a basic VFD, what type of parameters we might see, what we find on the nameplate, right? So basically very basic stuff. So if we needed it like more advanced, for example, it would be if we needed this motor to reduce voltage at a certain temp or whatever, just whatever parameters you might want to set, then you would need more advanced, right? So, and then let's see, I think that's pretty much it. I don't want to drag it out too long and bore you to death. So, oh, and the 4 types, the 4 stopping methods. Do you remember those? You say S-curve all the time, so that's the one give me. So the 4 stopping methods. So you got DC, brake, stop, right?
You have a coasting stop.
you have a coast that it's literally just called coast, and then you have a ramp, so you have a ramp stop, and then you have your S curve, or otherwise known as soft stop. So I think that's pretty much everything we've covered. So we went over the 3 main sections of an drive. We know the 4 stopping methods. So we're going to put a VFD in that motor control cabinet out there. And I've not played around with it yet either. But I'm sure you can input different parameters and see how they work and stuff. So that's going to be a cool lab to see, like, hey, we can control this motor with this VFD. You know what I mean? Instead of having to wire it up and use the push buttons and stuff, you can now have basically logic. Yeah, you'll have logic in there, so it won't be as difficult. So that's going to be our lab this week. And be sure to wear your proper PPE, because we're starting to hash down on that, which you normally do anyway. But, you know, just always have... Yeah, don't wear flip-flops in there. For the love of God, don't wear flip-flops. So just wear your boots and fire retardant clothes. And, you know, whatever else you might want to wear, like gloves. But that's not really necessarily required. And your safety glasses. Everyone should have a pair of safety glasses. Because Robbie has provided some, but at the same time, that's not really required. So, I personally would like to have my own pair anyway. So, everybody should have their own pair of safety glasses. And, you know, you don't necessarily have to have steel-toed boots, but you definitely at least need composite at the very minimum. And I know we haven't really had this problem in this class, but in other classes, people haven't been wearing their PPE, and that's a big deal. So now we're starting to say, if you don't wear your PPE, then you're not doing the lab. And if you can't do the lab, then you're going to get a 0 on that lab. So, fair warning, just wear your PPE, which I know you always do, but I have to say the same thing to everybody. Please wear your PPE, okay? And, yeah, so that's it. Whatever day you want to come do your lab. I don't know, you going to come tomorrow and do it? Okay. Well, I'm sure Robbie can help you. Yeah. Yeah, and I'll be here probably about 11, 12-ish. Somewhere between 11 and